Okay, you're live.
All right. This is where I usually start. There's an odd misconception in the computing world that writing compilers is hard. This view is fueled by the fact that we don't write compilers very often. People used to think writing CGI code was hard, and it is hard if you do it in C without any tools. So this is the basic idea of what Parrot is trying to do. You guys are going to have a hard time seeing the slides, sorry. Here, you can look at this one. So we're a single virtual machine that runs multiple different languages. So these are our big targets. But if you want a more accurate picture of what Parrot is all about, it's more like this. So we're not just interested in running the few big 5 languages. We're 6 or 7 or 8 or 10. We're interested in being a virtual machine that can host a variety of different languages, and particularly provide the power to create new languages very easily. So when I say that Parrot is a virtual machine for dynamic languages, I mean the basic idea of a dynamic language versus a static language is that you do things at runtime that in a static language you would do at compile time. So you have things like the ability to extend your executing code set on the fly at runtime, create classes at runtime, completely change the type system at runtime. Higher order functions, they're a function that takes one function as an argument and returns another function as the result. So you're essentially programmatically creating executable code on the fly. Closures, continuations, and coroutines. A closure is a subroutine that captures just a little bit of state in it, just variables, really, so that you can execute that subroutine anywhere and it still has those values stored within it. A continuation it captures more of the state. So it essentially captures it captures the entire state of the interpreter. It's like a reset button. So when you execute a continuation, you jump right back to where you were when you captured that continuation. And a coroutine it's a bit like the VCR of subroutines. So you can be playing along in your code, and you hit a point and you return a value. The next point that you call that same subroutine, instead of starting at the top again like you usually would, you start where you left off, and then you keep going. Some of the reasons why we started working on Parrot. Back in the days when we started Parrot, which was about 7 years ago, there wasn't very much respect for dynamic languages, PHP, Ruby, Perl. And we talked to companies like Sun and Microsoft because they had very powerful VMs, and explaining some of the things that we wanted to do with dynamic languages on the virtual machines. And they really laughed. Seriously, I've had these conversations with them. They laughed at the idea of creating a virtual machine for dynamic languages. In the 7 years since then, they've completely changed their tune. And now the JVM and the CLR, .NET, proudly proclaim that they support dynamic languages. They haven't quite gotten the full idea yet. They're still working on it. But just to have been in a place where we could change that public perception, it's very exciting. Another reason is I mentioned that our goal of inventing new languages. One of the reasons that the evolution of languages is so slow, and you'll find even languages like Perl 6, which supposedly is like, ahead of the curve, is the exciting new features that it's adding already existed in Lisp 40 years ago. So languages aren't progressing all that quickly. So our goal is to provide very powerful tools that will make it possible for people to push languages forward to the next stage of evolution. Portability is just the idea that we want a virtual machine that runs on many different platforms. Interoperability is the idea that when we have multiple languages all hosted on the same virtual machine, you can now use libraries from one language in another language. So you could use, say, a Python library in your PHP code or a Ruby library in your Perl code. This is very important because if you look at the way language use is going, more and more people that you talk to today, you'll ask them what language they use, and they'll say, well, you know, I use a little bit of Python, a little bit of PHP, a little bit of Ruby. And different languages are really better adapted to solving particular problems. Innovation is the idea that, well, I'll show you a few of the features, but Parrot is in a unique position because we're an open source project, because we're not tied to any company's corporate budget, to really drive forward the state of the art. And we've done that in several places. Things that a company might be too afraid to try because it's a risk, we can experiment with, and if it doesn't work out, we just chuck that chunk of code, and if it does work out, then we have a very powerful advance. So that's one of the reasons I really enjoy being on the project. So I'm going to show you I'm going to quickly show you a couple of the features that are completely different about Parrot than a virtual machine like JVM or CLR. So at the very core, Parrot is a register-based virtual machine. You may be familiar with the stack-based machine. How you perform a stack operation is you push some values onto the stack. Those are your arguments. You pop them off, perform the operation, push the result onto the stack, and on the other side you pull that off to get the result of the operation. So a register-based virtual machine, instead of a stack, you have a fixed set of registers. This is how hardware works underneath. So you store your values in those registers, your arguments in the registers, perform an operation, store the results in another slot of the registers, and retrieve the result there. Now this seems like a fairly simple modification, but in stack-based virtual machines, you spend a lot of time swapping things on the stack, pushing things on, popping things off, pushing things on, popping things off. And that's actually, that is execution time that you're spending right there. So this is a very low-level optimization. There's also the fact that the hardware underneath is register-based. So when you're jitting the code, which is an optimization, it's actually a quicker transformation to go from a register-based virtual machine to a register-based hardware machine than it is to have to translate the stack operations down to register operations. One further innovation that we added later is we found that, so we started off with a fixed set of registers, and then we figured out that even though, so registers in hardware are very expensive. You want the smallest number you can possibly get away with. Registers in software are completely free, so there's no reason that you have to have your fixed set of registers. So we changed it over to having a variable set of registers, an infinite set of registers, basically, but only as many as you need for the currently compiling subroutine. So each subroutine has an infinite set of registers. It may need 2 registers, it may need 500 registers. Never encountered one that needed that many yet, but but you have as many as you need for the current context and no more. Another very fundamental change, again, moving away from the stack-based virtual machine. In a stack-based virtual machine, when you want to call a function, you call the function, you push a return address onto the stack, and maybe then some arguments. When you're ready to return to the point where you called the function, you pop the return address off the stack and jump to it. So Parrot is a continuation-based control flow. You may remember I mentioned earlier that a continuation is essentially a reset button. So it's a subroutine that captures the entire state of the interpreter, and when you call that subroutine, it resets you back to the point where you captured it. So when you call, let's say you're calling subroutine foo from main, you capture a continuation in main, and then you pass that continuation which is a subroutine object, into foo. When you want to call bar, you capture another continuation object. This one includes the previous continuation object. You pass that continuation into bar. When you're ready to return, you just invoke that continuation. So you invoke the orange continuation to return from bar. You invoke the yellow continuation to return from foo. This is a pretty small innovation, in a sense. All you've done is translate a stack-based data structure into a linked list. But it provides some very important optimizations. When you're in a deeply nested context, let's say you've had 100 subroutines that called and called and called and called and called and called, and you want to return back to like the top level. With a stack-based virtual machine, you have to clean up the stack for each layer all the way back to the top. For a continuation-based virtual machine, all you have to do is invoke that one continuation at the very top, and you jump straight back. And then garbage collection takes care of all the intermediate continuations that you don't need anymore. I'm going to skip that, and I'm going to skip that. And this is a quick overview of the structure of Parrot. So I think all I'm going to show you today is the language examples here. So these are the tools that you use to compile your languages. So I'll skip that, and that, and that. So a lot of languages today use Lex and Yak for parsing. They're very primitive, but they work. What Parrot offers is a set of tools, we call it PGE, or the Parser Grammar Engine. It has the syntax of regular expressions, which is probably familiar if you worked in any of the common dynamic languages. But underneath, it's a full recursive descent parser, which is a very powerful, sometimes slow parsing technique. So my code example is Piney. All the languages implemented on top of Parrot have a code name of some sort. Piney is Python on Parrot. Cardinal is Ruby on Parrot because it's a red bird. So if you want to try out a little bit of code, you can download the full Parrot tarball from parrotcode.org. Piney is included in that tarball. Perl configure PL, that configures it. Make test will do the compilation and run the tests for Parrot. It's interesting. In the build process for Parrot right now, we depend on both Perl and Python. This is a dependency that will have to go away since we can't depend on ourselves, but for now they work. To build the language itself, go into the language's Piney directory and say make test. That'll do compilation and test the code, make sure it's working. So this is your very first Python script, print hello world. To run it, you say parrot piney.peer hello.py. That will change, so you can eventually just say piney hello.py. There's a bit of configuration there that we've done for some of the other languages and implementations, but not for Python yet. The implementation of Piney is 3 files. Piney.peer is the core implementation. It's 67 lines of code, half of which is documentation. And the core of that code is this. Create an HLL compiler. It's essentially an object for compilers. We implemented a lot of the core infrastructure that you need for creating a compiler as a library so that you can use it in any language implementation. Tell it the language is Piney, tell it where to find its parser, and tell it where to find its parser actions, which is how it translates the parsed stuff into something that it can actually execute. How much of this should I show you? Just quickly. So the parser, this is the parser rule. If you've looked at all at Python's defined grammar, it's going to look very familiar. This is Python's defined grammar, and that's the Parrot grammar. It looks a lot like regular expression syntax. You find like things like the star for repetition. The angles mean you're calling a rule inside of it. This is the rule that so when you do the parse, it gives you back a very raw tree. This rule here transforms that tree into an abstract syntax tree that Parrot can then interpret and run the code. So it's essentially just cleaning up the tree a little bit. And I won't show you the example here because, well, I'll show you quickly. So this is, when I talk about transforming the tree, so this is a start. You start with a number, 42. This is the parser rule, just digits for matching an integer. That gives you back a very raw tree. Then you write your transform rule, which looks like this. And that gives you back a cleaner tree. And at that point, that's all you need to do to implement your language on top of Parrot. Parrot takes care of the rest of it. This is what Parrot does internally, though. It transforms it again into another tree, transforms it again back into executable code, which in this case is a whole lot of work to get from 42 to 42. But it adds up quickly. So this is another example parsing an operation. So two numbers and an operator. So same process. Parse it, create a rough tree, transform it into a cleaner tree. But at this point, when you hand it off to Parrot, it's a lot more complex. So it transforms that cleaner tree into a much more complicated tree that does a lot of setup operations. So this is the complexity that Parrot is hiding from you by providing the powerful compiler tools. And that's the final code that you get from that one. So if you want to look at more examples, they're there in the Parrot repository. And we have probably about 2 minutes for questions, maybe 3. Yeah.
So it seems like a lot of people are concerned about virtual machines right now, which is great. So you've got the JVM, you've got Rubinius, and Parrot, and LLVM, and .NET that you mentioned. So it seems like this is one of those moments when people haven't figured out how to do something yet, and there's an explosion of possible solutions, and they're going to probably sort of fight it out in the wild, and one or two of them are going to dominate. How do you think that Parrot is positioned to do that? I guess, all of us Perl people, all we Perl people, are concerned about it getting done soon.
It will get done soon.
Do you feel like the timing matters? Do you feel like it'll be far superior?
I would like to have had Parrot done 3 years ago. I really would.
Yeah.
If you've ever seen Ben Collins-Sussman's Poisonous People talk, you'll know a lot of the reasons why it wasn't done 3 years ago. Timing does matter, and we feel it's very important to have Parrot done in the next year. But done means the 1.0 release, and it's still going to be a few years after that before, it's like Apache 2. There's an adoption cycle. There's a few years of adoption cycle. It won't immediately be the hottest virtual machine on the market. Parrot still stands in a very unique position. JVM and .NET are explicitly not targeting some of the features that languages like Ruby really need. They are absolutely uninterested in continuations and coroutines. So Parrot stands, and none of the other virtual machines are really quite targeting the same space. Like Rubinius is great for Ruby, but it's really only good for Ruby. So there's a few things. One of the things we're working on is LLVM integration. So you can take advantage of LLVM's optimizations from within Parrot. LLVM does not have a dynamic language strategy. They're only targeting static languages, and they have talked to us about being the dynamic language component for LLVM. So there's a few things. Another one of the areas that Parrot could stand to really take off is by providing concurrency tools that all dynamic languages can take advantage of without modifying their syntax at all. Concurrency is a very big hot topic right now as more and more more and more hardware machines go to multiprocessors, and most of the dynamic languages really aren't equipped to handle concurrency right now. So if they could just, don't modify their code at all, just plop it onto a different virtual machine, and suddenly they have full concurrency support, that's very compelling. Do we have time for one more question? One more question. Yeah.
For writing a language from scratch and like doing all this stuff, writing it in C or whatever is hard. Any wild guess for like, if I was going to write PHP and I was starting from scratch, it would take years. I assume it would take less than years if I did in Parrot. Any like wild guesses? It's probably a 2 to 1 or
Okay, so Patrick Michaud, who did a lot of the implementation of the compiler tools, he had a talk to give at a Python conference. And he knew he needed an implementation of Python for the conference, but he just didn't get time. And so the night before, he sat down with the compiler tools, and he implemented about half of Python. So it's a comparative.
Wow. Wow. And then the one other question that goes with that is, so then the only minus has to do with performance, that I assume performance won't quite be as good.
Okay, performance of a very, very simple language implemented straight in C, it won't be as good, but once you start adding in features like garbage collection, once you start adding in full control flow support and exception support and stuff like that, the performance is actually about the same.
Wow.
Maybe even a little bit faster, because with Parrot we can have 200 people, each from various different language projects, all working on optimizing the one piece that they need. Whereas if you're writing from scratch, it's really going to be unoptimized when you start.
Wow.
Well, thank you very much. Well, sorry, no problem. If you have any more questions, you can catch me after.